All right, this is chapter 4, section 4, number 45. We want a soda can. So we have to put a certain amount of soda in it. That's how much soda is going in it. Whoa. Let me try that again. This is how much soda has to fit in the can. But they want to minimize the surface area. Why would they do that? That's weird. Here's why. A soda can is usually made out of aluminum. And the more aluminum you use, the more expensive it is. So what you want to do is use the least amount of aluminum. How do you do that? Well, kind of you want the minimum surface area. And that's not exactly true because the top's thicker. We have other things going on. But conceptually, that should make sense. The minimum amount of surface area will make a cheaper can, make us more money. It's all about the money, right? So here's our can. What is that can made out of? It has a circular top, a circular bottom, and the side's actually a rectangle. I don't know if you see that. And we want to minimize the area. So my formula is A. And now again, I have to label stuff. What do cans have? They have radii. So the radius of this can I'll call R, and it has a height, H. Those are the only two dimensions of the can you really need. So I'll label it that way. Okay, what is the area of the circle? I know that. The area of this is pi r squared. The area of that is pi r squared. Uh-oh, what's the area of the can? I don't know. But as you can see, this distance right here, that's that distance. That's H. What's this distance of the can? As you unroll this can, that's going to be this distance. So imagine we cut the can right here, slice it, and we unroll this can and lay it out flat. The distance across the top is the distance around the can. That is the circumference, and everyone knows the circumference of a circle is 2 pi r. So the area of the side of the can is base times height, 2 pi r times h. Dun, dun, dun. So now I'm going to add these three things up. This plus this plus this is the surface area. So we're going to have two lids or two round parts. So 2 pi r squared plus a 2 pi r h. And am I happy now? Kinda not. Because what is our goal again? Our goal is to minimize the surface area. I want A to be a minimum. And then the questions ask, where do minimums occur? And you say critical points and endpoints. So we have to find critical points. The same thing over and over and over. So how do you find the critical point? We need the derivative. But you should see another problem. We have two different variables. We have to get rid of one. So somewhere in the problem, there's more information that we need. And here it is. The volume of the can is 354. How are we going to use that? How do you find the volume of a can? The volume of any shape is the area of the base times the height. So we need the area of the circle times the height. So the volume of this can is the area of the base, pi r squared, times the height, h. Excuse me, that's the volume of the can. So area of the base times the height. Well, we're told that that volume has to be 354. So we make 354 equal to pi r squared h. So here's our magic formula right there. Do I want to solve for the h or solve for the r? I think all of you can see it's easier to solve for h, right? If we solve for r, we have to square root. So if we solve for h, we get 354 divided by pi r squared. All I did, divide both sides by pi r squared, and I get that. And I take that value. and I plug it in for h. So now we have our beautiful area problem. 2 pi r times 354 over pi r squared, which nicely the pi's cancel, and one of those r's cancels with one of those r's, r, and we get this. 354 times 2, that's 708, I believe. And this r, if we move it to the top, that becomes r to the negative 1. And we are on our way. This is very similar to the last problem. Now we have to take the derivative. We can start moving faster. The 2 pi is a constant. I leave that in front. The derivative r squared is 2r. 708 is a constant. I move the negative 1 in front and decrease the power by 1. Woo! 4 pi r minus 708 over r squared. We're going to get our same common denominator that we've been doing for the last couple problems, I think. Or I've been doing it for the last couple problems. So we have 4 pi r cubed minus 708 over r squared. That's the derivative. Wow, Yoshida put the derivative sign in there. Okay, what are critical points? Where the derivative is 0. Where is this equal to 0? When the numerator equals 0. Oh, 708. I am on my game. Well, I'm not because I messed up, but I caught it. Whew, scary. I don't know what's wrong with me. Add 708 to both sides. Well, I almost did it again. Divide both sides by 4 pi. Cube root both sides. I'm going to get that on my calculator for an approximate value. I can do that. 708 divided by 4 pi. Raise that to the 1/3 power. That's about 3.8 approximately. Okay. Now we want to know if the derivative is undefined, and that occurs when the denominator is 0. But once again, that's not a critical point because that's the end point. The radius, the smallest the radius can get is 0. That's the end point. And so we're going to, that's not a critical point. So we're going to ignore that. So we are in the situation again where we only have one critical point. If that is a relative max or relative min, then it's an absolute also. So once again, we're going to make a nice, beautiful sign chart with radius. That's bad. With radius and the derivative, because we want to know if the derivatives change from positive, negative, negative, positive. This is going to be cube root of 708 over 4 pi. Pick a number to the left. I pick 1 and I pick 10 because that's what I choose. Plug in 1. Okay, I can get this. I can get this. If I put a 1 here, that's about 12-ish. 12 minus 708, definitely negative. The bottom's always positive. That's negative. Then I plug in 10. 10 cubes, 1,000. This is about 12. It's about 12,000 minus 708, definitely positive. And I'm pretty much done. And here's what I need to say. We have a relative minimum at this point here that I circled because A prime changed from negative to positive at that point. And since that's the only relative extrema, it must be the absolute minimum also. So the question, find the radius and height. So we found the radius. Here's what our radius needs to be. What's our height have to be? Well, to find the height, we use this formula. I'm going to use a different color here. This is our height formula. We know the radius, plug that in there, and you can get the height. And that's the answer. And that is number 45.